All right, so a true statement. Well, like I said, guys, all year long, we're going to see different pictures, and you're going to have to set up true statements to be able to solve for a variable. So we had yesterday or 2 days ago, I think it was maybe yesterday, we had two parallel lines in the transversal, and we had to set up a true statement with that. Now we have a triangle. We have to set up a true statement using this. So what do we know, since these are in the angles, what do we know about the angles of a triangle? They all three will add up to be 180. So it'd be true to say this plus this equal 180. So x plus 2x plus 2 plus 3x is equal to 180. And then from there, we could solve for x. But I just had to set up a true statement. Are we all okay with that? How many got it right? Good. Okay, that's a lot. Awesome. We combine like terms. So we'd have 1x plus 2x plus 3x would be 6x. So we have 6x plus 2 is equal to 180. And then we continue to solve for x from there. All right. I'm not going to do that because I just want to get started on the lesson. Any questions on that one? Awesome. Good. Good. A lot of you got that correct. Okay. All right. So yesterday we learned some more with probability. A lot of you really struggled in this class with tree diagrams. I think I must not have explained it very well to this class because my other hours didn't struggle at all. They understood it completely. So I must have just not explained it very well. So we're going to go through a problem real quick. So guys, the tree diagrams are easy. Like, tree diagrams are really easy. It's just a way to list the possible outcomes of events. So I mean, some of you weren't getting the right idea with these. So I'm going to go through this one on yesterday's worksheet. Okay? So if you want to get out your worksheet from yesterday, that would probably be good. So, recall that really a tree diagram is just a way to model a series of events. All right, so for example, the series of events I'm going to be talking about first is tossing 3 different coins. Now, you don't toss a coin. Now, I'm not, honestly, a lot of you were doing this yesterday. I saw this on this problem on like 8 people's worksheet in this class. When you toss a penny, do you get a penny when it lands? We're talking the outcomes of a penny. So when you toss a penny, you either get a heads or a tails. You don't get a penny when you toss a penny. I mean, technically you do, but we're talking possible outcomes. So I saw people trying to do tree diagrams saying penny, nickel, dime. Well, that's not an outcome. You don't list, tree diagrams are listing the possible outcomes of when you toss something or do something. So that's not how tree diagrams work. So let's list out the possible outcomes. So first of all, event 1 is tossing a coin. It doesn't matter what kind of coin. Event 2 is tossing another coin, getting a heads or a tails. So we're talking a heads or a tails, a heads or a tails. Tossing this and getting a third coin, getting a heads or a tails. So now a tree diagram is just a way to see the order, the ways, the number of different ways you could get heads and tails with all 3 things. So let's focus on 1 first of all and just make our tree diagram. We're going to ignore the part where the probabilities are weighted. So we're just going to make a regular old tree diagram. So in event 1, I'm listing the outcomes of event 1. You toss a coin, you get a heads or a tails. So you get a heads or a tails. No questions on that. No questions on that. Okay, so moving on to the second event. Now, let's say you tossed a heads on the first one. We're moving on to the second event. You toss the second coin, and after you got the heads, you're going to either land on a heads or a tails on the second event. So let's say I landed on heads. My second toss, I'm either going to get a heads or a tails. So I'm in a pot. Does that make sense? So you're saying that after 2 tosses, we either got a heads and a heads or a heads and a tails. Does that make sense, everybody? All right, now let's go back in time, back to the first toss. Let's say that on our first toss, we got a tails. Let's move on to our second toss. When we do that, we toss our second coin. We're either going to get a heads or a tails. So you're saying I could have also got a tails on the first one, then a heads on the second one, or I could have got a tails on the first one and a tails on the second one. Does everybody see how the first 2 events took place? Okay, these are just the possible ways that the events could have taken place. You're all okay with that? You didn't quite get it yesterday, so did that make more sense today? Okay, good. Then let's move on to our third event. It's tossing a third coin. So heads, heads. When you toss a third coin, you're either going to land on heads or tails for your third event, right? Now let's say that on the first event you got a heads, the second event you got tails. When you toss the third event, you're either going to get a heads or a tails. So do you see how it's just listing? You could have got a heads, heads, heads. You could have got a heads, heads, tails. You could have then tossed a heads, tails, heads, or a heads, tails, tails. Just a way of listing the possible ways that you could have got the answers for all three events. Okay, moving on. So tails, heads, on the third event, you're either going to get a heads or a tails, right? Let's say we would have got a tails on the first, a tails on the second. On the third event, you're still going to get a heads or a tails. No questions on that. So how many possible outcomes? Well, you can count the ends of your tree diagrams to see. Because I don't want to have to list out heads, 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 however I could. Heads, heads, heads. I'm only going to do it for a second. Heads, heads, tails. Heads, tails, heads. Heads, tails, tails. Do you see how this is taking forever? You don't need to do that because you can just use your tree diagram. So the total possible events was 1, 2, 3, 4, 5, 6, 7, 8. There's 8 total possible. Any questions? 8 total events. Okay, now in the problem though, now if this was not weighted probability, if it was equally likely to land on heads versus tails, we would just count the total number possible, which is 8, and then we would see how many times these events happened. But it says the probability of getting a heads is greater than the probability of getting a tails. So the probability of getting a heads is 4/5. So then if it's way great, so do you guys understand that that means 4 out of 5 times you're going to land on heads? Okay, so how many times are we going to land on? So for heads, 4 out of 5, we're going to land on heads. Then how many out of 5 do we land on tails? 1 out of 5. Guys, that's just a probability. 4 divided by 5 is a percent. 1 divided by 5 is a percent. But I'm going to leave it like that. All right, so then let's see here. Now it says, find the probability of landing on 3 heads. Oh no, this happened a second ago. Attention. So it says, what's the probability of landing on 3 heads? The only place in the whole tree diagram of landing on 3 heads is right here. Heads, 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 right? So landing on heads, then heads, then heads. But isn't it way more likely to land on heads than tails? Yes. So now the probability, since these are independent events, is of all 3 events happening is taking the individual probabilities and multiplying them. So we want to know the probability to land on a heads, then a heads, then a heads. So we multiply the individual probabilities. So that would be, I need more room. Probability of landing on heads is 4/5, right? So 4/5, the probability of landing on heads is 4/5. The probability of landing on heads is 4/5. Then once you calculate that, that's the probability you'll land on a heads and a heads and a heads. So I need my calculator, I don't have it, so somebody's gonna have to do it for me. 4/5 times 4/5 times 4/5. What's the percent?
It's
Percent? 51 point what? Perfect. So 0.512, which is 51.2% chance. So isn't it way, that's crazy. It's way likely that we're going to land on a heads, 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 right? That's crazy out of all those outcomes. But it's because those heads were weighted. 4 out of 5 times you're going to land on heads. Does everybody understand that? You're sure? You didn't get it yesterday. Do you get it now? Okay, let's do this one. What's the probability of landing on at least 1 tails? So I'm going to look at my tree diagram, and I'm going to list out when that happens. At least 1 means the least amount is 1 tails. So if you look at this, we have heads, heads, tails. Isn't that one? Ding, ding, ding. Then we have heads, tails. So those 2 are this one, and these ones are, right? And then tails aren't all these ones that land on at least 1 tails? Yes. So really, there's only 1 that doesn't land on tails, right? Isn't there only 1 that doesn't land on tails? Heads, heads, heads. And we knew that probability was, does everybody understand how every single other outcome besides heads, heads, heads has at least 1 tail? Yeah? Okay. So then if the probability of landing on heads is 51.2%. The rest would be at least landing on one tails, right? So you'll take 100% minus 51.2%. That's the easiest way of doing it. So somebody do it. 100% minus 51.2%. And that would be the probability of landing on at least one tails. 40 what?
48.8.
48.8. So there's a 48.8% chance of landing on at least one tails. Does everybody see how I did that? Now we could have added up the individual probabilities of every single one of those. That would have taken a long time. I actually did it on the worksheet like that, but I thought about it and like, oh, this is way easier. Okay. Do you have questions on that? Okay. No? Then, okay. Then let's move on to today's lesson. All right. All right, so today we're going to be doing 3-3, which is unions, intersections, and complements. Pay close attention today to the little details. It's going to be a little bit different than the probability we've been doing before. We're going to get in depth with unions, intersections, and complements of events. So remember, the probability is a percent from 0 to 100 that indicates how likely an event is to occur. So once again, probability is a percent from 0 to 100%. That indicates how likely it is for an event to occur. So we know we can calculate probability like this, 1 over 2. You take your calculator, 1 divided by 2. So that's 0.50, which means 50% likely to happen. Now here are some vocabulary words that you have seen already and you're going to see especially today. So you might want to, if you want to take a picture of that, you can. You don't want to write it down. I mean, that's why we have technologies to make education go better, quicker, whatever. So sample space. The sample space means the set of all possible outcomes on a test, on the end of levels, on my test. It's going to say list the sample space. Yeah, it means all possible outcomes, okay? So you're going to see it usually denoted as a capital letter. So notice how I said A is equal to, and then those little brackets, those fancy brackets, are just a way of saying we have a set of these values. These are our outcomes. So those brackets are just a way to say these are my outcomes. You'll put your outcomes inside. So you put this, you'll put your outcomes inside those little brackets. Those brackets look like this. That's what this set is. So once again, sample space is a set of all possible outcomes. So for events. So what if I said, name the set of Miss Christensen's first hour class? That would be, you guys would all be in the set. Does that make sense, everybody? I said, list the set of chocolate lovers in Miss Christensen's first hour class. I would have you raise your hands and you would be the people that get to join the set. Does that make sense, everybody? Okay, that would be my sample space is the set of all possible outcomes. Sorry, all possible outcomes. Then subset is a smaller set of outcomes from the sample space. So I just lied to you. When I said this, when I said everybody in Miss Christensen's class is the sample space, that was true. But subset is a smaller set of outcomes from the sample space. So this was my chocolate example. I got in head. So then if I said, okay, you guys are all in my first hour class. You're all in the sample space. Now raise your hand if you love chocolate. Then only 10 of you raised your hand and I pulled you guys out. This is where you would go into this subset because you come out of the huge sample space into a smaller subset. A smaller set of outcomes from the sample space. Does that make sense, everybody? So the sample space was the whole class. The smaller piece was only the people that like chocolate. Does that make sense? Subset versus sample space. And then complement. You'll see this today. Complement means everything that isn't in the subset. So once again, everything that's not in this little piece. So everything left out of the subset would be the complement. So everything that isn't in the subset. Everything that's not in the smaller piece. So all the people that didn't like chocolate, that were not in here, would be in my complement. Everything that was left out of my subset. So these are the ways you'll see it written. Honestly, I'm not kidding you. Every single test is different. Every single book's different. It's just the same. It means the same thing, different ways of writing it. So not B means the complement of B. Everything not in B. This little squiggly B means the complement of B. So everything not in B. They all mean the same thing. This line, this bar over B means the complement of B. Everything that's not in B. And then that B mini C means B complement, everything not in B. So these are just different ways to denote the complement, which means everything not in the smaller subset. And I will on the worksheet write them different ways. And on the test, I'll write them different ways. Do you understand how it means the same thing though? Okay. All right, am I okay to go on? Okay. All right, so for example, let B be the sample space. Here's our first example. Let B be the sample space. So this means all possible outcomes are in this set. B is equal to the set of 1, 2, 3, and X. That's my sample space. Now here are some examples of some subsets. Remember that subsets mean smaller sets of the full sample space. So A is a subset because it only contains 1, 2, and X. We left out what? 3. You see how that's a smaller piece of the bigger one. And then C is also an example of a different subset, just an example of a totally different subset. 1 and 3, because that's only a small piece of my entire sample space. And then D is also an example of a subset. It's just a smaller piece of the full sample space. So these are subsets. So we're going to go through and find a complement. So the complement of A means everything not in A that was in the sample space. So we had a 1, a 2, and an X. What did we leave out of our sample space? 3. So the complement of A would be the set of 3. Questions on that? Okay, so then with this one, we're asked to find the complement of C. So that means everything not in C that was in the sample space. So we had a 1 and 3. What did we leave out? A 2 and a X. So this would be the set of 2 and X. Does it make sense? Yes or no? Okay. And then D complement. So bar D means D complement. So everything not in, I need to not cover that, but I need more room. Everything not in D. So X is in D. So what's left out? 1, 2, and 3. All right. Any questions on that? We're all okay with complements then. Okay. And subsets and sample spaces. Okay. All right. Moving on. All right. So let's do another one. Given the sample space, S is equal to 1, 2, 3, 4, 5, 6, and 7. Find the subset of numbers greater than 3. So we're doing a subset. So I'm just going to call it, so I'm just going to do a subset. So find the subset of numbers greater than 3. So that just means a smaller piece of the entire sample space, but for numbers greater than 3. Because our numbers that are greater than 3 include 3. No, so all the numbers greater than 3 in our sample space would be 4, 5, 6, and 7. So 4, 5, 6, 7. Not too bad, right? So find the subset of odd numbers. So now we're doing a smaller set of the entire sample space. So odd numbers, you look at your sample space. What are odd numbers? 1, 3, 5, and 7. 1, 3, 5, and 7. There's our subset. No questions. Make sense? We're all good. Okay. All right, so we know how Venn diagrams work. Now, yesterday we had a problem that this would have been helpful to have this lesson before that problem, but that's okay. So a Venn diagram just helps you categorize data. So you'll be given multiple sets. You'll put them in a Venn diagram. And remember that Venn diagrams make it easy to see where the elements are related. Because remember, if we have 2 events, now you can do Venn diagrams with more than 2 events, but really in this class, for the most part, we'll stick with 2 events. We have our first event, we have our second event. The things in here are only in event A. The things in here are only in event B. And then you put it in here where it's intersection. It makes sense. It's in both circle A and B. It's where it's the things that go in event A and B. So if it's in event A and B, you will put it in the middle. We know how Venn diagrams work, right? Remember our example of our red ties, green ties. There was a red and green tie, it went in the middle. And then we have our sample space. So sometimes, guys, there's going to be things in our sample space that do not fit in our Venn diagrams. Well, it's still in the sample space, so it's just floating out here. And we even saw that with the green tie, the green tie and red ties. Remember how there was a blue tie? Did it fit anywhere in here? No, but it was still there was still a blue tie in the sample space. So it went outside. I called it floating in the abyss. So hopefully you remember that. All right. Here we go. All right, so last 2 things, and then we'll just start practicing. These are the last 2 things you have to understand. Unions and intersections. So union is the set of elements in either A or B. So once again, union, and you'll see it denoted like this. They're not going to write out union very often. They'll usually write it as a capital U. So a capital U, and it won't have a little tail. It'll just look like this. So the union means the set of elements in either A or B. So here's a keyword, the keyword or. So if they're in A or B, then it's in the union. So I call it friendly. This is a little trick I came up with to help you remember. So does everybody see how this looks like a smiley face? Yeah? Does everybody see how if I put little dots, it looks like a smiley face? So it's friendly. It's very friendly. So unions are friendly. They allow anyone in. So anyone in event A, anywhere, and anywhere in event B are welcome to come. So they're friendly. Unions are friendly. Now, intersection is an upside down U. And so does everybody see how they look just opposite? This means intersection. Intersections are the set of elements in both A and B. Now notice the keyword is and. So if it says and, that means it's in both A and B. Now these are not friendly. Does everybody see how it looks like a frowny face? Not friendly. This one's way pickier. They're not very friendly. It's kind of like that close group of friends that won't let anybody into their group of friends. They're not friendly. And that's the only people allowed in is if they're in the intersection. Does that make sense? So if it's A and B, it's only in the intersection that's allowed in to the set. Does that make sense? When it was friendly, everybody was welcome in set A and B. Intersection was only in here. Does that make sense, everybody? Okay. No questions? Okay. All right, so let's do this for first example. So given set A is equal to ABC, given set B is equal to MATH. So we are going to put this in a Venn diagram. So I'm going to call this event A, I'm going to call this event B, and then we know, of course, that this is the intersection of A and B. So let's go through and put these things from set A and B into our Venn diagram. All right, so let's just start with A. So we have an A in our set. Is there an A? We got to check. Is there an A and B? Yes, so it's in both. So it's got to go in the intersection. But I'm going to move on. B, is there a B in that set? No, so it's only an A, so it's going to go right here. Then I'm going to put a C. Is there a C in this one? No, so it only is in set A. Now we've taken care of A, move on to B. Left over was an N. We know it's not in A, so it only goes in B. Then there's a T, also not in A, only in B. And then there's an H. Everybody see how I categorize my data in my Venn diagram? So now we'll go through and answer these questions. So I'm going to scroll up because we'll use our Venn diagram. So it says, find A union B. Is this the friendly one? Yes, so everybody in A and B, in A or B, is welcome. Friendly one. So everybody in here is welcome, and everybody in here is welcome because it's friendly. It lets everybody in. So this would be the set of BCA, order doesn't matter, BCA, MTH. They were all welcome. Questions on that? Yes?
So that is like your sample space?
Yes, in this one, my entire sample space did get to join, but if there was something out here, which we'll do an example, that didn't get a join, because it's only in A or B. Does that make sense? Yeah, good. Now let's find A intersect B. This is the not so friendly one. The only people allowed are the elite, the intersection. So who's allowed into this set? A. All right, any questions? Okay. All right, now let's find A complement. A complement, remember that means everything not in A. So that means everything that's not in A. So is B in A? Is C in A? Is A in A? Yes, right? So what's all the things that is not in A? MTH, very good. Any questions on that? Not too bad, right? Now that you know what you're doing. And then this one. It says find the complement of A intersects B. So find the complement of A intersect B. Now with something like this, you'll want to work from the inside out. So first of all, before we find the complement, that means everything not, we need to find what's in the set of A intersect B. Well, we already know A intersect B, right? It's A. So for this part, I'm just going to write right here, we know it's A. So what's everything not in that set? B, C, and T, H. Did everybody see how I did that? I worked from the inside out. I'm going to say it again. First of all, I did the A intersect B. We already had done that one. Well, if we hadn't, we'd say where do A and B intersect? It's right here. Now we want the complement of that. So I'm looking, this is what I'm looking at, but we want the complement. Everything not in that. So that would be B, C, and T, H. Very good. B, C, and T, H. Are you all okay with that? All okay with that? All good. Okay, awesome. All right. Quickly, let's do this one. So it says, given the sample space, S is equal to 1, 2, 3, 4, 5, 6, 7, given events A and B. So we have these two subsets. We're going to put them in our Venn diagram. So this one is the last. Okay, we're almost there, guys, and then I'll let you work. So event A, let's put it in our Venn diagram. So this is A. Well, this is B, and then inside here is the intersection. So let's list it. There's a 1 in A, and B is there a 1. So it's just in A. 2, 2. Yep, it's in both, so it goes in the intersection. So we've taken care of A, and B, we need to put in 3, 4, 5, right? Now let's look at our sample space. Are there other numbers floating in the abyss? We have a 1, we have a 2, we have a 3, we have a 4, we have a 5. So what's floating? 6 and 7 on the outside. Okay, you see how it's floating? Still in the sample space. Okay, so let's find A union B. This is the friendly one. Everybody in A and B are welcome. But if they're not on A and B, not welcome. So they're only somewhat friendly. So A union B, this is the friendly one. So everybody in A or B are welcome. So it's going to be the set of 1, 2, 3, 4, 5. Questions? Find A intersect B. This is the not friendly one. Only the elite get to join. So which number? 2. This is A and B, and A and B would be 2. And then let's find B complement. So that means everything not in B. So I'm going to look. Now I got to be careful. 2's in B, 3's in B, 4's in B, 5's in B. So I'm going to cover up all that. Now look at the entire thing. What's everything not in B? 6, 7, and 1. Very good. And then let's find A intersect B, the complement of that. So I'm going to work from the inside out, kind of. This one doesn't have parentheses, but we could put parentheses around A intersect B. So what is A intersect B? 2, right? A intersect B is 2, right? Now we want the complement of that. So what's everything that's not 2? 6, 7, 1, 3, 4, 5. Very good. Does everybody see how I did that? This one's the last one. Find A union B complement. So this is the friendly one. So if they're in A and B complement, they're welcome. Now these are the hardest ones. This is the best way to do it. I'm going to list out A. A is 1 and 2, right? I'm going to list out B complement, so that means everything not in B, and then I'll unite them. Does that make sense? So what's everything B complement? Means not in B. So that's 1, 7, and 6. So B complement is 1, 7, and 6. Now this is a friendly one, so as long as they're in A or B complement, they're welcome. So our final answer would be 1, 2, 7, 6. Now notice how I didn't list 1 twice. Was there 2 1s in our sample space? No. Okay, so this is how I list it. Any questions on that? We're all okay with complements, intersections, and whatever. Okay, awesome. We're almost there. All right, so given these standard deck of cards, let's practice these probabilities. and then I'm done. So look how close I am to being done. So I know you're feeling this was kind of a long lesson without me letting you work, but every single problem was in depth, so I couldn't just, you know what I mean, without teaching the whole thing. All right, so given this deck of cards, these are what a standard deck of cards are. You're going to have quite a few problems today with standard deck of cards, so pay close attention to this problem. I'm going through it for a reason. So in a standard deck of cards, you have your clubs, clovers, hearts, and diamonds. Notice half are black, half are red. Does everybody see that? The hearts and diamonds are the red cards. This is like every deck of cards. The clovers and spades are the black cards. Does everybody see that? These are my face cards. I have a jack, queen, king. Face cards, jack, king, queen, jack, queen, queen, jack, queen, queen, king. All right, so what's the probability of drawing a card of 2 or 3? So in the full deck of cards, how many cards do we have total? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 cards, right? 13 cards up here. So 13 plus 13 plus 13 plus 13, right? So that's 52 cards total. So I need to know that to be able to do the probability. So total, you need the total for probability, because we know probability is the number of outcomes divided by the total number of outcomes. So how many cards are a 2 or 3 in the entire deck? 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 52. So that's the probability. Recalculate it. 8 divided by 52. 153. So that's a 15.3% chance of landing on a 2 or 3. Does that make sense, everybody? Okay, let's do another one. What's the probability of a black card? How many black cards do we have in our total deck? 13 and 13, right? So 26 out of 52. So calculate that. But you could just see it also. But you could do 56 divided by 52. Can anyone just look at it and see what's the probability we'll draw a black card? It's going to be what? 1/2, 50%. Did you get 0.50? Perfect. So 0.50. So that's 50%. Does everybody see why you could have just looked at it? I mean, you could have done the math, but isn't half the cards black? Okay. All right. What's the probability? I'm going to change colors. What's the probability of drawing a diamond? How many diamonds do we have? 13. So 13 out of 52. 1/4, which is 25%. There's a 25% chance of drawing a diamond. Now this is the harder one, but it's not too bad. You just have to actually think. What's the probability of drawing a black card or an 8? So does that mean everybody is welcome if they're a black card or an 8? Yes, right? So how many black cards do we have? 26. There's 13 here, 13 here. So we have 26 black cards. And that includes those 8, right? So you won't double dip on those. We already counted those ones right here, right? Now how many more 8s do we have? 2 more. So we have, that's how many cards? Good, 28 cards. So 28 cards are either black or 8s in our deck. So 28 over 52. Calculate that probability for me. Somebody. 0.53? 0.538? Okay, awesome. So 53.8% chance. Okay, questions? Not too bad, right? We're all comfortable with today's. Was way easier than the other days, right? Okay, awesome. Good. So finish the worksheet. Finish the worksheet.